Hello and welcome to helpyourmath.com. In this video, we're going to take a look at simplifying expressions using the properties of exponents. First, let's review these properties. First up, we have same base multiplication. So we see we have a base a being raised to the power of x and a base a being raised to the power of y. When we have the same base being multiplied, we can simplify this by adding the exponents. The second property is power to a power. So this would look like a to the x to the power of y, and this would give us a to the x times y. We would multiply the power. So power to a power, we multiply. Same base times same base, we add. The distributive property of exponents over multiplication, there's also one for division as well. It would technically be the same, but we would say if we have a times b inside parentheses being raised to the power of x, this would be a to the x times b to the x. Similarly, if we had a over b raised to the x, we would also distribute that exponent to both the numerator and the denominator. Then within this distributive property, if a or b had exponents, then it becomes power to a power. It'd be a to its power to the x, and then you would apply the power to a power, and you would multiply the exponents. If we have same base division, now we're looking at the same base, a to the x over a to the y, and we would subtract the exponents a to the x minus y. In my last video, I went over what happens, like what if y is bigger than x? How do we handle that? That brings us into these negative exponents, and I talked about the certain strategies I use to deal with them. So the first strategy is if I just have a to the negative x, we kind of treat the exponent as two parts, the negative, which is -1, and x. The negative part says take the reciprocal of the rest of this thing. The reciprocal here would be putting a under 1, and we'd say 1 over a to the x. In the last video, I talked about what we do if there's a negative exponent in the numerator or if there's an exponent in the denominator. If you need to review that video, this would be a good time to pause and go to that video, and then don't forget to come back here. Other properties, we have our invisible exponent. Our invisible exponent is 1. So a to the first is the same as a, or a is the same as a to the first. If a does not equal 0, but it's some other real number, and it's being raised to the power of 0, that equals 1. And 1 raised to any power at all is 1. Before we look at our monster expressions, let's talk about strategies that I use. So if you want to be consistent, this is what I suggest. I do have students who say, well, can I do a different order? Absolutely. As long as you're applying these properties correctly, you can do any order you want. If you're looking for consistency, this would be a good set of rules to follow. So our pre-step, if there is no fraction, but there are negative exponents, create a fraction by putting the entire expression over 1. We saw that take place in the last video, just to kind of help us figure out, because usually the directions say, write your answers with positive exponents only, so we would need to take care of those negative exponents, put it over 1, that way you're creating the fraction that's then going to help get rid of the negative part of the exponent. Okay, next up, if we have parentheses, we want to distribute the exponents that are outside the parentheses to all the factors or bases inside. The biggest mistake we make here is we lump a number factor with whatever factors behind it. So if it said 2x and then it was being raised to the third, sometimes we make the mistake of just saying 2x cubed, but that's not true. 2 is its own separate factor. It should also be cubed. So you just want to be very careful with the numerical factors, because they are their own separate factors and they have their own separate exponents. Usually we would just see the number with no exponent, in which case it has an invisible 1 exponent. Okay, next up, move any base with a negative exponent. So a base with a negative exponent in the numerator will have a positive exponent in the denominator. A base with a negative exponent in the denominator will have a positive exponent in the numerator. Once you've switched the location of that base, the exponent becomes positive because you've taken care of the operation that is signified by the negative exponent. Number 3, combine all same factor bases in the numerator. That would be same base multiplication. And any same base factors in the denominator, also same base multiplication, by adding the exponents. Then we're going to combine all same base factors between the numerator and denominator by subtracting the exponents. My tip, so we don't end up with any negative exponents, is you always subtract the larger exponent by the smaller exponent, and whichever one had the bigger exponent, that's where the remaining factors would go. So if you have, let's say you have, I'm going to put a 2 up there just so we have something. If we have 2 factors of x in the numerator and I have 6 in the denominator, when I go to subtract, I'm actually going to do 6 minus 2, which is 4. Those 4 factors of x would be in the denominator, right? They're going to replace this because we're going to get rid of the 2 that were in the numerator. The x to the 6th had those 2, but it also had 4 more. So my suggestion is wherever more factors of that base were, that's where the remaining factors will go. And lastly, we just want to keep in mind that our numerical bases are normal numbers. We do normal number things with them. If it says 2 over 8, and then we have this x to the 4th, we'll say, this is the fraction 2 over 8. We don't do any subtraction, right? These aren't exponents. These are normal numbers. 2 over 8, those share a common factor of 2, and it would be 1 over 4x to the 4th. So we just want to keep in mind, normal numbers, we do normal number things. I see in our first 3 examples, we don't have any parentheses, so we don't need to worry about doing the distributive property of exponents. We're going to start with step 2, which says anything with a negative exponent will have a positive exponent if it's in its other position. So negatives in the numerator will be positive exponents in the denominator. Negative exponents in the denominator will be positive exponents in the numerator. And notice in our first 3 examples, we don't have any parentheses to worry about, so we're not going to apply any distributive property. We're going to jump right to step 2 that says any factor with a negative exponent wants to move its location. I see a negative exponent on this x to the negative 3rd and this w to the negative 8th. Otherwise, anything with a positive exponent stays where it is. So staying in the numerator is that w squared, and staying in the denominator is that x to the 5th. When we move this x to the negative 3 down, it becomes x to the positive 3 because we've taken care of the negative. And when we move it, everything's multiplication, so it would be multiplied to whatever's in the denominator. W to the 8th will move up with that positive exponent. Now we're going to go across the numerator and see, do we have same base? Yeah, we have w squared and w to the 8th. When we have same base multiplication, we add the exponents, giving me w to the 10th in the numerator. In the denominator, I have 5 factors of x and 3 more. That's a total of 8 factors of x. Since w and x are not the same base, we are done with this first question. From here, I do suggest, I forgot to say it before this one, but pause the video. See if what you come up with for your final answer. Keep in mind that final answers should have at most one of each base. So a final answer shouldn't have an a over here and an a over here. Somehow you can combine those factors of a. Okay, so let's see what happened. In our next example, we have a 2 with a positive 1 exponent. A to the 4th is fine where it is. B to the negative 7th wants to move down. C to the negative 2nd wants to move down. A in the denominator is fine. B to the negative 4th wants to move, and that's the only factor in the denominator that wants to move. And again, it's because it has a negative exponent. So I'm going to just rewrite this now with every factor having a positive exponent. 2 stays, a to the 4th, good. And that b to the negative 4th will move up, becoming b to the 4th. This a stays. The b to the 7th moves down. The c squared moves down. C cubed is already down there, and it has a positive exponent, as does a to the 5th. Now you'll notice I'm kind of just taking the factors that I moved from the numerator, just kind of like placing them in the middle of the denominator. That's okay because this is all multiplication, so we can put things in any order. The commutative property says that that's okay. Going across the numerator, I don't see any same bases, right? I have a 2 and an a and a b. I'm going to just rewrite those for now, and then I'm going to look to the denominator and combine my same bases down there. This is one where I do this in multiple steps, but you can combine in a single step if you feel comfortable with this. Down here, I have 1 factor of a. This is a to the 1st with that invisible 1 exponent. I have 5 more factors of a. The denominator now has 6 factors of a. There's only 1 b to the 7th, 1 base b, so it would just be b to the 7th. And then I have a c squared and a c cubed. That would make c to the fifth because we add them. I'm not done yet. So that was just using same base multiplication. Now we're going to look at same base division. Do we have any same bases between the numerator and denominator? We do. The 2 is all by itself. It's the only numerical factor. So we're going to leave 2 alone. With the a's, I have 4 factors of a in the numerator and I have 6 in the denominator. Because there are more factors of a here, right, we could think of a to the 6th as a to the 4th times a squared. Well, the a to the 4ths would cancel, and there'd be a factor of a squared still in the denominator. We also have a base b in the numerator and a base b in the denominator. I have 4 b's in the numerator. I have 7 in the denominator. We could think of those 7 b's, we could break it up into b to the 4th times b cubed, right? And the reason we would do that is because then the b to the 4ths would cancel each other out, and we have that b cubed still in the denominator. B cubed down here. C to the 5th, it's just c to the 5th. So we would just leave it like that. Now, this is how I handle the same base division when we have more factors of, a or b in the denominator. If you want to use same base division and subtract the exponents, you can absolutely do that. You would have 2, and then next to the 2 would be an a to the negative 2. Well, that a to the negative 2 would need to move down to the denominator so it can have a positive exponent. So just to save a step, that's why I kind of just think about where are there more factors of whatever base. That's where the remaining factors will go. And now we see we have 1 of each type of factor, and we are done. Last up, we have, this one's nice. Well, wait, the a squared, since this is the same factor as this just becomes 1 and 1, so that was nice. Now I have 5 factors of b in the numerator. I have 7 in the denominator. It looks like I could take this b to the 7th and just kind of break it up, b to the 5th times b squared. The b to the 5ths will cancel, and I have a 1 over b squared in the denominator. And that would be my final simplified expression for that third example. Just to look at a few more, because we have not yet seen those parentheses, pause the video, see what you can do with this one. Okay, let's take a look. So how many unique bases do we see in the first set of parentheses over here? Well, 2 is its own unique base, and x is its own unique base, so we are distributing the 3 to 2 different bases. 2 currently has an exponent of 1, and then it becomes power to a power when we distribute the 3. Well, 1 times 3 is 3, so we end up with 2 to the 3rd. We don't take the exponent and multiply it to the base. That's not what that means. We multiply it to its exponent, which is currently invisible 1. So we now have 2 cubed. Then we have x squared to the 3rd. Now you can multiply the 2 and the 3 because the 2 and the 3 are both exponents, and we get x to the 6th. And then here we want to do, this is power to a power. Here we have x to the 8th. And then in the denominator, we have 6x to the 5th. Let's clean up this numerator. So, separately, I kind of deal with the numbers. 2 cubed is 2 times 2 times 2, which is 8. And then x to the 6th times x to the 8th, that's same base multiplication. So we would add the exponents. We get x to the 14th. And now we have normal number 8 and normal number 6. Normal number 8 and normal number 6 have a common factor of 2. So we want to divide these by 2. Again, we don't use properties of exponents for normal numbers. Now we're going to look for common factors, divide them both by 2. And that's going to leave us with 4 over 3. And what about these x's? I have 14 factors of x in the numerator. I have 5 in the denominator. We could think of x to the 14th as x to the 5th times x to the 9th, right? Because that's same base multiplication. We could add the exponents. Those would cancel. Those 9 factors of x are in the numerator. Okay, and then the 4 and the 3 are fine because we can't simplify them any further. I only have 1 base x. This is the final answer. And lastly, what is going on with this one? Wait. First of all, this is like a freebie because this whole thing is being raised to the power of 0. This whole thing becomes 1 because this thing raised to the power of 0 just equals 1. That was nice. And it's done because there's something else up there. We can ignore that thing entirely. Next up, we're going to distribute this negative 4. How many unique bases are there in that first set of parentheses? So how many times am I distributing the negative 4? I hope you said 3. 3 has its own invisible exponent of 1. it becomes 3 to the negative 4th. Then we're going to distribute to a to the negative 3rd. Negative 3 times negative 4 is positive 12. And lastly, we distribute to the negative 1. We get positive 4. In the denominator, how many times am I distributing the negative 2? I am distributing it 3 times. We get 6 to the negative 2, a to the positive 2, and b to the negative 12. So far, so good? Okay, I hope that was a yes. What we're going to do next, anything with a negative exponent, we're going to switch its location so that that 3 to the negative 4, we're going to move it down to the denominator where the exponent becomes positive. Same with this 6 to the negative 2, I'll just preemptively move this one up because it will have a positive exponent in the numerator. And then the a I'm going to leave here because it has a positive exponent. B has a positive exponent. Down in the denominator, a squared has a positive exponent. Oops, b wants to move up into the numerator. Okay, so now we're going to go across. I'm going to be consistent with what I said. So I'm going to work across first, and then I'm going to look top and bottom. First of all, 6 squared. First of all, 6 squared is 36. That's 6 times 6 is 36. There's only one base a in the numerator, so I'm just going to write a to the 12th. B to the 4th times b to the 12th. That's same base multiplication, so I add the exponents and I get 16 factors of b. In the denominator, 3 to the 4th, that's 3 times 3 times 3 times 3. 3 times 3 times 3 times 3. This would be 3 times 3 is 9. Another 3 times 3 is 9, and 9 times 9 is 81. So I have 81 a squared. Okay, so now I'm going to think about 36 and 81. Well, they're both divisible by 9. So I'm going to divide both 36 and 81, right? We don't subtract those. We divide them by dividing out a common factor. 36 divided by 9 is 4. And 81 divided by 9 is 9. Then I have 12 factors of a in the numerator. I have 2 in the denominator. We could think of a to the 12th as a to the 10th times a squared. Those cancel. We have a to the 10th, that's in the numerator. B to the 16th is the only base b. So here we have our lopsided final answer for a to the 10th, b to the 16th over 9. These have been examples of applying the properties of exponents to simplify these monster expressions. Thank you for stopping by.